So what we want to do, we want to show you like the basics. This is the basic stuff that you can do, like when you want to do probabilistic damage tolerance analysis, is to use this master curve. Master curve is what has been traditionally used by many other codes around the world. So we want to show you how to do it. And most important is we want to show you how to do it in Excel. So you can understand like what is happening in all these different codes that is doing PDTA analysis. So let me do this. What I want to do is I want to show you what is on the folder that you got. So when you look at this folder, so we have, of course, you don't have the PowerPoint, but you have the PDF. So you have access to the PDF, and then you have 4 different folders. You have Excel examples. So for any example that I'm going to be showing for the Smart this afternoon, in the next 20 minutes when you grab me out, we have this Excel example, but I'm not going to have time to go through all of them. So I create a video where you can go and watch that video. Let me go into the videos. So there is 3 different videos. There is a master curve, basic, POF. So this is the very first one. We're going to cover this one today. We have master curve random initial crack size and master curve random fracture toughness. What is this video showing? The first one is how to compute POF for a deterministic analysis. So once you sample your initial crack size, once you sample your fracture toughness, how do you compute POF? And we have this in a Smart and in Excel, so you can compare the results and you should get exactly the same result. Then we're going to have another video that is, what about if I'm doing variations on initial crack size? Like how do I sample that master curve when I have variation on initial crack size? So again, we have a video, we have a solution in Excel, and we have a solution in Smart, and you should get exactly the same answer again. And then we have what happened when KC, when fracture toughness change. How I do variations on residual strength when that KC is changing. So you're going to have access to all these 3 videos with the same accent that you are listening right now because I record those. So feel free to watch them later, okay? That's what you get in that folder. Here we have the Excel examples. So you can go into the Excel examples and take a look to those. And then the example problem that we're going to be having today, we're going to do one with hypergrowth. So I'm going to give you a quick introduction to hypergrowth. Then Nathan is going to take like a deeper dive. And then I have like an additional supporting material that is this other example for a wing spar. So we have 5 different examples. We're not going to go only through 2, but then with the help of the videos, you're going to be able to go through the additional 3, okay? We're always available. Feel free to shoot an email if you want to continue the discussion or anything that you may need, okay? So what I just described to you is everything that I have here. So we're going to do probability of failure review. I'm going to show you how do we do the master curve interpolation. The best way to do this is with the basic POF example, but also we have another examples in there that you can go through them, okay? Many times. Third time that we're going to repeat this, so you remember for the test at the end of the day, the probability of failure is defined as the probability that the maximum stress per flight will exceed the residual strength, okay? You see that the residual strength is function of KC, so when we do variation on KC, this is going to change. And it's function on the initial crack size, so you see that when we do variation on initial crack size, so this side is going to change. And then the EVD is this loading that we compute using the Smart, or you can bring into the analysis, and you have the master curve residual strength, which I'm going to show you how to do variation in a second. I show you this on the previous slide. Is just the POF is the probability that the maximum stress will exceed the residual strength. So every time that we cross this curve, we define that as a failure, and you see that the failure increases through time because the residual strength is reducing, okay? But residual strength is not always the same. Residual strength can change. Why? Because fracture toughness changes, because we have variation on geometry. So this curve shifts up and down every time that we try to solve this problem, okay? So what is the assumptions of master curve? So master curve is very good. It has been used many times. but it has like some few assumptions that sometimes I call them like limitations. Only fracture toughness, initial crack size, and EVD can be random. If you want to have variation on the geometry or variation on DADN, you cannot use the master curve approach. You're going to need to use a different approach. But it's very good to do assessment on what is the situation on your fleet, okay? The other assumption is only one spectrum that is representative for the entire simulation. So you generate one set of spectrum and you use that one to grow your cracks and to compute your EVD. So this is like the assumptions that we have on master curve. Any questions here? Okay. So the approach is you generate an initial crack size and a fracture toughness. You bring your spectrum and your geometry and material properties. You give those either to avgro, NASGRO, any internal software that you're using at Boeing, Northrop Grumman, or your company is. And then what do you want to get back is the crack size versus time and the residual strength, okay? And you can put that one into a very simple file that I'm gonna show you. So we have an A versus M file where each column represents flight numbers, flight hours, crack size, or residual strength, okay? Just a column-based file that you will see how simple it is. So I introduced this on the previous slide. From the fracture mechanics, we know that fracture toughness is equals to the stress times beta times the square root of pi a. If I want to solve for the residual strength, it's just going to be Kc divided by beta. This is the geometry parameter times the square root of pi a. Okay, so we get this curve that I have in here. Now, if I want to have variation on those, so what we do is we take the residual strength curve and we normalize that one into this alpha parameter. So you will see, if you're familiar with prof, you're going to see that prof use this as an alpha. An alpha is just beta times the square root of pi a. So you will see like this curve. And we use this curve because it allows us to have variation on Kc. So I can do samples on Kc, then divided by the residual strength, so I can have different values of alpha. Then I can generate a fracture toughness realization, which is going to be my sample. Then I can generate back my residual strength curve. The only thing that I need to do is to take this alpha and pass it here to divide, so I can have my residual strength again. Here, the residual strength of the sample is higher than the residual strength of the master curve, so that's why this is higher. So at the end, what is the equation that we use when we do this? So the residual strength for the given sample is going to be equals to the ratio between Kc of the sample to the Kc fracture toughness of the master curve multiplied by the residual strength of the master curve that was provided to the analysis, okay? So that's what we do every time that we want to generate a new residual strength curve for a new realization, is just to do this operation, okay? So I already talked about the Excel files, but let's get into the first one, which is the basic POF, okay? So before I show you that one, so how you can solve these equations, how you can, for example, you have variation on initial crack size and fracture toughness. So you just integrate this one from 0 to infinity. This one is the crack size, so that's why it starts in 0. And then from minus infinity to infinity, the fracture toughness. And you just do the conditional expectation on this, and you can get your POF. So you can integrate, or you can use sampling, in this case, Monte Carlo sampling, okay? If you have 3 different realizations, so you do your 3 realizations, and then you add them up and you divide by the number of samples and you compute the expected value. So that's what we call the expected value. So it's very simple. So every time that you have variation, you just grab your value of initial crack size, you grab your value of fracture toughness, you compute your POF, and you repeat that 1 billion times until you get your expected value that doesn't have too much variation, and you repeat the analysis. But you use AMIS, which we're going to take a look in a second, you only need like a few thousands in order to compute converge POF results. So I'm going to open this example. This is in Excel again, and this is just to show you how to do master curve. We're going to follow these examples, these steps, which is you extract the flight number, crack size, and residual strength from the fracture mechanics run. So you go and you run avgro, nasgro, your internal fracture mechanics, and you extract this information: fly number, crack size, and residual strength. Okay, and then you're gonna bring those into Excel, for example, and you're gonna find the value for your initial crack size. So let's say I want to have a 005. So you take that 005, you locate that one on your data, you extract that section that you need, you remove the offset, and then you compute your POF. It sounds very complicated in these 4 steps, but I'm going to show you in Excel, so you will see that it's very simple to do. So I'm going to go here into our folder, which is Intro to Probabilistic Master Curve. I'm going to go to Excel, Basic POF, and I'm going to open my Excel. So just be a little bit patient until I open Excel. It's here. So I told you, step number 1. So from your fracture mechanics, extract fly number, crack size, and residual strength. So I have that one in there, okay? So if I plot my crack growth, is this blue line that I have here, and if I plot my residual strength versus time, is this blue line that I have here, okay? Then I'm gonna have an initial crack size. So for this case, I assume that my initial crack size is at 005. So what I'm gonna do is I'm gonna locate the 005. It can be any value that you want. But in this case, I'm gonna locate my 005. I'm gonna take all the way down here until failure. So you will see that I have my 005 starting at 25,000 with a residual strength of 93 KSI square root of inch, and then all the way through failure, okay? So this is the step 3. So you locate this value and you extract all the information all the way through failure. Then what I'm gonna do is to remove the offset. So I see that this crack size starts at 25,000. So what I'm gonna do is I'm gonna take this 25,000 and I'm gonna subtract it to all these different values. So I'm gonna have 0, 1,000, 2,000, 3,000, because I start this analysis starting growing this crack at 005. So the 005 belongs to a time equals to 0 all the way through failure, which is 20,000, okay? And then the last thing that I have to do is I will take this POF and I'm gonna compute, I'm gonna take this residual strength and I'm gonna compute my POF. Do you remember that I showed you the generalized EVD equation? So it's this one that I have in here, where X is my residual strength, B is my location, and divided by A, which is my scale, okay? So it's each value of residual strength, so 93 minus 14 divided by 0.8, negative, take the exponent, 1 minus that, and I should get my POF, okay? And you will see the POF computing by hand in here. So if you see, this is gonna be 1 minus the exponent of the residual strength minus the location divided by the scale, and I get the POF. And I compare that value with my value from SMART, and then I plot those two together. So you see I have my SMART value and I have my Excel value. Excel just go through 0 here because the double precision of the machine doesn't allow me to compute that one using Excel, but you see that here they're exactly the same, okay? Let me do this in SMART very quick. So in SMART, I'm gonna go File, Open, and from my Intro to Master Curve, I'm gonna go to the Excel example problems, basic POF, and I'm gonna open my SMART file, okay? So in the SMART file, I'm doing only one sample. I'm not doing any variation, only one sample. My crack growth, let's take a look to this file. This is the file that I told you, you go and run it in avgro, nasgro, and then you put it in this format, okay? Where you put, what is the fracture toughness that you use in nasgro, avgro, LifeWorks, any software that you're using, okay? What is the yield strength? We didn't have into account yield strength, so I just put a 1 there. What is the hours per flight? It's 1, so I have a relation of 1,000 flights is equals to 1,000 hours. And what is the failure criteria that I'm gonna be using? This case is fracture, okay, KC. You can use KC, you can use next section yielding, or you can use the minimum between those two, okay? And then you have this column, which is flight number all the way through failure. You can have it every 1,000, every 500, whatever you output, you can put it here, okay? Then this is a true crack. So I only have results on the C direction. So you see that there is no results on A, A1, or C1. There is only results here. So you just paste the results of your crack here and then X in the other ones. Let's think that you have a corner crack. So you have a corner crack, so you're going to have values on A until that corner crack transitions into a true crack. When that transitions, you put an X, and then you have your residual strength by KC, and here we just put the same one because we didn't compute it by next section yielding, okay? But smart is going to take only this column. If you put here minimum, M-I-N, N as a Nancy, so it will take what is the minimum of these two in order to compute your POF, okay? So you can export this file, or you can open it, you can plot it. I already showed you how to plot it, okay? You can browse and bring another file. On the material, I have it just custom. We're going to talk about the material, the probabilistic material database in a second. But here I just put it as a custom where my fracture toughness is 34.8. And then I just put a high value of yield strength.
4 minutes.
4 minutes? Get ready, man. Okay. Then my initial crack size, 005. Loading, I just put my EVD values. I don't have any inspections. I do the run. You just take a snap, and I get my results. And you see that these results is exactly the same as this one. Maybe you cannot see it there, but if you want to see it, you just go to show my POF, and you can see that at 6,000, I have 4.59 E16. So at 6,000, 4.59, that's the value of a smart. So what I have in this column is just extract from a smart. So you can see that we have exactly the same results, okay? So it's very simple, okay? The problem is to be able to make this efficient as we have been doing it, okay? So I have 4 minutes before I get tackled here. So let me go back to my presentation. We have another one where we have variations on KC. Take a look to that one. We explain step by step like how you do it. And then do it in a smart as well and see that you will get exactly the same results. I have a step by step how to do it. Then if we want to use hypergrowth, so remember that hypergrowth uses a constant amplitude and ODE formulation, so I can get my crack growth. So I'm going to use this problem, a true crack, a corner crack in a hole. I'm going to be using Newman-Raju corner solution. So on the GUI, you have that example. You can just load it. What is going to be different is on the growth, you're going to have master core, but it's no user provided. It's going to be hypergrowth. And then you're going to choose here Newman-Raju. What is the width? What is the thickness? The hole diameter. Okay. And then you can run that one. I select here the material database, and Nathan is going to be using exactly these problems. It's just to introduce a little bit to the hypergrowth. And then when you do your run, so you get your results, okay? Same thing, we are doing a master curve, but to generate the master curve analysis, we use hypergrowth instead of the user providing that one, okay? That was the only difference that I did here. So we reviewed the probability of failure and EVD calculations. We did master curve interpolations also using the master curve, using the A versus N, and we use hypergrowth, okay? There is some supplemental material here, so feel free to go through random crack size, random KC, and do those examples. And the beauty is you're going to do it in Excel, you're going to do it in Smart, so you're going to be able to get exactly the same results and see how the code works using Excel. So with this, I will stop.